In this video, we're going to look at our first signals. So we're going to use the wave generator as a function generator to create a signal that we're going to measure on channel 1. So we're going to connect the scope up between the wave generator and channel 1. Then we're going to turn on a sine wave. We're going to look at it with the scope. We're going to play around with the vertical and horizontal scale, adjust the windows so that we can see both the function generator and what the scope measures, and then we'll play around a little bit with the function generator. In the next video, we're going to pay attention to the most important aspect of using a scope, and that's about triggering. The first step is we're going to connect the output of the wave function generator into channel 1 of the scope. Remember, if we look along the side here, we can identify which is the wave function generator. We're going to use W1. We're going to go into channel 1 of the scope. And W1 internally is automatically referenced to ground. And so we just need to make sure that the 1 minus of the scope is referenced to ground as well. And the way we're going to connect the output of the wave function generator into the +1 of the of channel 1 and of course -1 of the scope into ground is using the small little female to female jumper. And so we're going to connect the wave function generator into the plus channel 1. So here's the solid orange that goes into the yellow. Great. Now we've connected the +1 of the plus of channel 1 into the wave function generator, but because we're doing a single-ended measurement, we have to connect the 1 minus of the scope to ground. And so we'll just use the adjacent channel here, and any one of the black wires are all connected to ground, so it doesn't matter which one we use. Plug it in, and we're done. So we've got the channel 1 plus goes to the wave function generator output for channel 1 for wave generator 1, and 1 minus the minus side of the differential input goes to ground. And now we're going to be able to measure on channel 1 the voltage coming out of the wave function generator. Let's take a look at that on the scope. We've got the scope connected. We turn on waveforms. We bring up our scope, and we see the typical kind of starting screen. Remember, in order to see something on the screen, to trigger the scope to start it going, we're going to push the run button, and there we go. And now we're going to look at the function generator. We go over to the welcome screen. There's a little plus. We're going to come in. That opens up all the different instruments available. We're going to go to the wave generator. And if you notice, here are the different options. We're going to select a sine wave. At your leisure, you can come back and play with some of these other waveforms, which we'll do at the end of this video. We're going to use default conditions, kilohertz, volt amplitude, and now we're going to say run. And that's going to output the signal on the function generator. Now, before we go back to the scope, remember rule number 9. Rule number 9 is before we do a measurement or simulation, always think about, anticipate what you expect to see. So we're going to see a signal, a sine wave waveform with an amplitude of 1 volt, so it'll be about 2 volt peak to peak. It's going to be a millisecond period, and it'll be a nice looking sine wave. That's what we expect to see. So let's go back to the scope, and so we access the different functions that are on the instruments on the top bar. We go to the scope, and here is our sine wave waveform. And let's see, we're on a 500 microseconds of division, and we're at a half a volt per division. And so sure enough, here's our amplitude of 1 volt, so 2 volt peak to peak. And let's see, here is 1 cycle, and 1 cycle is half a millisecond, a whole millisecond. Sure enough, exactly what we expect to see. That's great. Now, there's one glaring thing that you notice. Look, we have all this noise on the screen. Where is this noise coming from? Now, the scope itself is always sampling at 100 megasamples a second. So it's every about 10 nanoseconds, it's taken another discrete voltage measurement. In order to display on this time base, we're taking all of those 100 megasamples a second, and if you see over here, we're converting those into 1.6 megasamples a second. So we're averaging together, about 70 or 80 different data points to create each one of the data points on this scale. But we're still looking at all that 100 megasamples a second. And the scope is displaying for us the peak, max, and min voltages for each point, and that gives us a feel for how much high frequency noise there is. We'll explore this in a couple of later videos because it's a really interesting area. But for now, we can turn that off and only look at the average value of those 80 some points with a really simple feature. So remember, we said the gears are all settings. So for channel 1, for that gear, we come over here and we say, oh, I don't want to see the noise, just turn it off. And now we're only looking at that average value. And this is one of the ways of filtering out high frequency noise, exactly what we're doing. Now, before we go on, you always want to be thinking about consistency tests. I mean, you can never prove you're right about anything, but I think you can. I think the more consistency tests you look at that are consistent with your understanding, the more confidence you have in your understanding. So before we proceed, let's take a quick look at this noise. Let's turn it back on. Now, it's hard to distinguish, okay, I see the noise on top of the sine wave, but I want to see just the noise. So I'm going to create a waveform from the function generator that is just a DC voltage. So I go to the waveform generator. Instead of the sine wave, let's use DC, and we're literally going to have zero output. The waveform generator is generating a 0-volt signal. And what is that going to look like on the scope? It should be just a flat line. Let's go to the scope. Well, our flat line, yeah, it's a flat line, but we've got the noise on top of it. I'm going to expand the scale a little bit so we can see that noise with a little bit more detail. And there is our noise. And now let's take a look at what influences. If that's really pickup noise, then if I change the shape of the wires, I will change the amount of pickup noise. So here's our scope, and here are the wires. And notice what happens. Here is channel 1 plus and channel 1 minus. We're looking at the voltage difference. If I make this loop area larger, look what happened to the noise. Got a lot more noise. If I make that loop area smaller, look, I can filter out some of that noise. I get less pickup. That's the general feature of it's a lot of the pickup because of that loop, so it's magnetic pickup in this case. And so by using a smaller loop area, I'm getting less magnetic field, AC magnetic field pickup from the RF environment, very noisy environment. Later on, we're going to look at the spectrum of this noise. We're going to try to figure out where is that noise coming from. But you can see it's clearly related to the wires. That's why, in general, we always say keep the signal and return, or the plus and the minus wires, as close together as practical in order to minimize crosstalk. In this case, crosstalk between the outside world and channel 1. So now we recognize where it's coming from. We accept, okay, given these jumper wires that we've got, we're stuck with this noise. If we want to see a signal where this is interfering with it, then we're not going to want to use jumper wires. That's where the 10x probe is going to come in. But for now, all we're looking at is sine waves. We're just playing with the scope features. Perfectly okay to use the jumper wires that we've got here. But it's still a little bit annoying seeing all of that noise. And so what we're going to do is, you remember we said, okay, if you go to that gear setting, you have all these different settings to go. We're going to turn off that noise now that we understand where it's coming from. And on this time scale, we don't really care about the high frequency noise. We'll let it be filtered out. And there it is. Now let's take a look at our sine wave. So we're going to go back to the wave generator. We're going to go and select the sine wave. It's turned on, it's running, and now we go back to our scope, and oh my gosh, we're way off scale. This is where vertical scale is really important. So our range is 100 millivolts. Remember, this is situational awareness. Our signal is a volt amplitude. Our scale here is half a volt. We are way off scale. So we want to go back to about 500 millivolts of division, and there's our nice sine wave. So first step is we're going to play with a vertical scale. Adjust the vertical scale. If we make it less sensitive, 2 volts of division, we're going to have just a tiny little signal appearing on the screen. And if we go to 200 millivolts, then we're going to just about peg it to the top, plus minus 1 volt on the scale. We're not changing the signal coming in, and it turns out that we're really not changing the amplifier of the scope. All we're doing is changing how that signal is displayed on the screen. Let's go back to the half a volt. And then finally, let's change the horizontal. And so right now we're at half a millisecond of division. So if we zoom out, we'll be able to see more cycles. Here we'll have 10 milliseconds. We ought to see, remember, rule number 9, we go to 10 milliseconds, we ought to see 10 cycles per division. Oh my gosh, there they are. And if we zoom the other way, we can go to 1 millisecond full scale. Let's see, there are 10 divisions full scale. So I want 1 millisecond, so that's going to be 100 microseconds a division. That'll be 1 millisecond full scale. We'll see 1 cycle. Let's see. Hey, there it is. 1 cycle. So it's consistent with exactly consistent with what we expect to see. So there is our sine wave. Play with the vertical scale and the horizontal scale. Those are two really important scales that we'll be using for every measurement. Now let's go back to the wave generator, and maybe we'll take a look at some other kind of waveforms. If we change the frequency, let's see, if we go to 5 kilohertz, let's go to 10 kilohertz. 10 kilohertz, 100 microseconds, that means that we're going to see a cycle every 100 microseconds. Let's go back to our scope and take a look at that. And sure enough, here we are at 1 millisecond division. We got 100 microseconds for a period. We get 10 of these cycles per division. Exactly what we expect. Now, we've been going back and forth between the waveform and the scope. There's another way of displaying these two screens at the same time. And if we just go all the way across on the top bar, we'll see we have some options of how we display things. What we're doing now is we're looking at a different tab for each waveform. If we want to tile them to have them both on the same screen, we click that box, and now we've got the scope up above and we have the waveform generator down below. So we can come along here and we can change this. Let's go back to our 2 kilohertz, and we can make a change here and we can see the impact directly in the scope in real time. That was the square wave. Hey, we can look at sine wave, and we can look at some of these other waveforms as well. So at this point, you're now ready to play around, take a look at all the waveforms, change some of the parameters here, adjust the vertical scale and the horizontal scale in order to see that waveform appropriately in the scope window. And don't worry about or change anything related to the triggering. In the next video, we're going to look at that very important feature.